11:38 a.m., Cape Canaveral, a clear, cold morning in Florida.
The 51st mission of the Space Shuttle, the 25th launch. It was supposed to be routine.
Mach 1.92. Altitude 46,000 feet. 73 seconds into the flight.
Total signal loss. A fireball in the upper atmosphere, 7 astronauts gone.
It wasn't a detonation. The shuttle didn't blow up. It was torn apart by aerodynamic forces.
The teacher in space mission, Krista McAuliffe, was on board. The whole world was watching.
Millions of schoolchildren saw it live. The visuals were confusing. 2 boosters flying away from a cloud of steam.
And the silence? Mission Control didn't even know what to say. Obviously, a major malfunction.
The G-forces at breakup were around 20 gigaseconds. The orbiter disintegrated instantly.
But the crew cabin? The cabin was reinforced. It survived the initial breakup.
That is the darkest part of the physics. The cabin remained intact during the fall.
They likely survived the breakup. They had emergency air packs. 3 were activated.
They fell for 2 minutes and 45 seconds. Terminal velocity, 200 miles per hour. The wreckage was scattered over 500 square miles of the Atlantic Ocean.
The cost, replaceable hardware is one thing, but the shuttle program was frozen for 3 years.
Every pound of payload into orbit cost $10,000. That day, we lost billions in hardware alone.
NASA's reputation was obliterated. The dream of routine space travel died right there.
The investigation started before the debris even settled. We need to look at the footage.
Focus on the right solid rocket booster. The SRB, that's where the money trail leads.
At T+0678 seconds, less than a second after ignition, a puff of black smoke.
Right at the aft field joint. It shouldn't be smoking. That's a seal breach.
The smoke stopped. The hole plugged itself with aluminum oxide. Slag.
A temporary fix, a band-aid made of burning rocket fuel. It held for 50 seconds.
Then came the wind shear, the strongest ever recorded for a shuttle launch.
It buffeted the stack. It shook the plug loose. That was the point of no return.
It buffeted the stack. It shook the plug loose. That was the point of no return.
It was pointed directly at the external tank, the giant orange fuel tank.
Specifically the hydrogen tank and the strut holding the booster to the shuttle.
The strut failed. The booster rotated. It smashed into the wing and the tank.
Liquid hydrogen meets liquid oxygen. Rapid combustion. The structural load spiked.
And the Challenger was flying sideways at nearly twice the speed of sound.
It shredded. The orbiter just snapped. Physics took over.
But why launch on that specific day?
The temperature. It was 18 degrees Fahrenheit that morning. Deep freeze.
The launch pad was covered in icicles. The photos are insane. It looked like the Arctic.
Engineers measured the surface temperature of the boosters. It was 8 degrees.
Standard operating procedure says no launch below 53 degrees.
They launched at 18. That is a massive violation of the thermal envelope.
This wasn't an accident. This was a gamble with 7 lives.
The O-rings, the rubber seals inside the booster joints, they are the key.
We need to talk about Morton Thiokol, the contractor who built the boosters.
They knew. Their engineers were screaming about this the night before.
Do not launch. That was the recommendation. It was explicit.
Rubber gets hard when it freezes. It loses elasticity. It can't expand.
If it can't expand, it can't seal. If it can't seal, the gas escapes.
And if the gas escapes, you have a blowtorch on the side of a bomb.
The logistics of the launch schedule were brutal. NASA was pushing for 24 flights a year.
Impossible. The turnaround time was too tight. The hardware couldn't take it.
Congress was watching. The budget was on the line. They needed a win.
Launch fever. The psychological need to push the button.
They ignored the ICE team. They ignored the booster engineers.
Rockwell engineers also warned about the ice falling on the tiles.
NASA management said, the ice is an unknown, not a concern.
In engineering, an unknown is a no-go. You don't launch on hope.
The timeline of the disaster is short, but the timeline of the error is long.
It goes back to the design of the joint itself. It was flawed from the start.
A design chosen to save money. to make the boosters shippable by train.
Exactly. The boosters were built in Utah. They had to fit through tunnels.
So they built them in segments. And segments need joints.
And joints are weak points, especially under pressure.
The Titan rockets didn't have these joints. They were one piece.
But the shuttle was a political machine as much as a flying machine.
Spread the contracts, build in every state, create jobs,
and create failure points. That segmented design was the first domino.
The second domino was the budget cuts in the 1970s.
And the third domino was the weather on January 28th.
When you stack bad design, low budget, and freezing cold,
you get catastrophic failure. The probabilities catch up with you.
The crew never stood a chance. The abort modes didn't cover this.
No ejection seats, no escape pod. Once the boosters lit, they were committed. And that one thing was a quarter-inch of rubber.
A quarter-inch of rubber, and a room full of managers saying, "Go."
The physics of the crash are brutal, but the psychology is worse.
Let's dig into the mechanism. How did that seal actually fail?
We need to open the technical schematics of the field joint.
And I want to look at the teleconference transcript from the night before.
The data was there, the charts were there.
But nobody was looking at the graphs. They were looking at the clock.
Get the blueprints. We are going inside the booster.
Block 2 is going to be heavy. Prepare the autopsy.
I'm ready. Let's trace the burn. Let's look at the anatomy of the kill. The solid rocket booster is not a single tube. It's 4 steel segments stacked on top of each other. Where they connect, you have the field joint. It uses a tang and clevis design, essentially a giant tongue and groove system. Inside that groove, you have 2 rubber O-rings, a primary and a secondary. They are the only thing stopping burning fuel from leaking out.
And this design was problematic from day one. Thiokol's original proposal promised a seamless casing, but they switched to segments to secure the contract. Why? Because Thiokol is in Utah. To get the boosters to Florida, they had to use trains, and trains have to pass through tunnels. The size of a railroad tunnel dictated the design of the spaceship. Logistics dictated the engineering.
Here's the mechanical flaw: joint rotation. When the solid fuel ignites, the internal pressure hits 900 psi. Instantly, the steel casing actually balloons outward like a water hose. This causes the metal joint to bend and open up a gap. The O-ring has to be fast. It has to spring back and fill that opening gap in milliseconds. If the rubber is warm, it's fast enough.
But on January 28th, the rubber was frozen solid. We need to go to the teleconference the night before. This is the smoking gun. Engineers from Thiokol, specifically Roger Boisjoli and Arnie Thompson, presented data showing that below 53 degrees, the O-rings could fail. They fought for hours. They told NASA, if you launch, you could lose the ship.
NASA's response was hostile. Lawrence Malloy, a manager at Marshall Space Flight Center, literally attacked the data. He asked, "My God, Thiokol, when do you want me to launch next?" "April." He was looking at a schedule, not a thermometer. He ignored the basic laws of thermodynamics. Cold rubber loses its memory. It doesn't bounce back. It stays compressed.
This is the moment the system broke. Thiokol's senior management asked for a 5-minute recess. They went offline. The general manager, Jerry Mason, turned to his vice president of engineering and said the most infamous line in engineering ethics history: "Take off your engineering hat and put on your management hat."
That phrase killed 7 people. They overruled the engineers. They signed the launch waiver. The next morning, at T-0, the boosters ignited. The cold O-rings were too stiff to move. Hot gas bypassed the primary seal and soot blew past the secondary seal. For a fraction of a second, the shuttle was flying with a hole in its side.
But then luck intervened. Aluminum oxide, residue from the fuel, clogged the hole. It formed a temporary slag seal. It was fragile, but it was holding. They cleared the tower. They went through the roll maneuver. For 58 seconds, they were actually okay. The gamble almost paid off.
Then they hit max Q, maximum dynamic pressure. This is where the air resistance is strongest. On this specific day, they hit the worst wind shear in the history of the program. The shuttle was battered by high-altitude crosswinds. That vibration shattered the fragile slag seal. The flame returned.
It was a blowtorch aimed right at the strut holding the booster to the giant external tank. The telemetry shows the pressure dropping in the right booster. The pilot, Mike Smith, likely saw a flash or felt the yaw. The last thing recorded on the voice loop was Smith saying, oh.
The flame burned through the strut. The bottom of the booster broke free and swung outward, pivoting around the top attachment point. The nose of the booster smashed into the liquid oxygen tank. At Mach 1.92, the structural failure was instantaneous. The orbiter was thrown sideways into the airstream and ripped into pieces.
It wasn't a random accident. It was the normalization of deviance. NASA had seen O-ring erosion on previous flights. Instead of seeing it as a near miss, they redefined it as an acceptable risk. They got used to being lucky until the day their luck ran out.
And the cost of that luck was calculated in milliseconds. The crew cabin separated cleanly. It continued upward on a ballistic arc, reaching 65,000 feet before gravity took over. The physics of the fall are terrifyingly simple. What goes up must come down. The investigation, led by the Rogers Commission, brought everything into the light. Richard Feynman, the Nobel Prize-winning physicist, cut through the bureaucratic fog with a single, devastating demonstration. During a televised hearing, he took a piece of the O-ring material, clamped it in a C-clamp, and dropped it into a glass of ice water.
It was theater, but it was brilliant. After a few minutes, he pulled it out and unclamped it. The rubber didn't bounce back. It stayed flat. He looked at the cameras and said, for a successful technology, reality must take precedence over public relations, for nature cannot be fooled. That moment destroyed NASA's defense.
The technical verdict was clear: a catastrophic failure of the field joint due to low temperature. But the engineering fix was actually straightforward. They redesigned the joint with a third O-ring and added a capture latch to prevent the metal from bending open. The hardware was fixable. The culture was the real problem.
And the financial fallout was astronomical. The replacement orbiter Endeavour cost $1.7 billion to build. The redesign of the boosters added millions more. But the true cost was the loss of the commercial space dream. The shuttle was banned from carrying commercial satellites. The business model of the program collapsed overnight.
From a survival standpoint, the Challenger disaster changed how we look at escape systems. The shuttle was launched without pressure suits for the crew, just flight overalls and a helmet. They had no parachutes, no ejection seats, and no way to separate the cabin from the stack. They were locked in a death trap from the moment of ignition.
After Challenger, NASA mandated pressure suits for launch and entry. They installed a telescoping pole so astronauts could bail out if the orbiter was in a stable glide. But here is the brutal truth. None of those systems would have saved the Challenger 7. At Mach 2 and 46,000 feet, there is no escape. The only survival strategy was not to launch.
The legacy of Challenger is written in safety protocols. Today, launch fever is a recognized psychological trap. Engineers have stop-work authority, the power to halt a launch if they see something wrong, regardless of the schedule. We learned that redundancy isn't just about having two computers, it's about having two independent opinions.
But we still see echoes of this today. In every industry, finance, tech, construction, managers still pressure engineers to cut corners. Normalization of deviance is everywhere. When you ignore a small warning sign because nothing bad happened. Last time, you were walking the same path as NASA management in 1986.
If you are an engineer, a pilot, or anyone working with high-risk systems, remember January 28th, physics is unforgiving. It doesn't negotiate. If the numbers say no, the answer is no, no matter who is yelling at you to say yes.
And if you are in management, remember the cost: 7 lives, billions of dollars, a national trauma. The price of ignoring the experts is always higher than the price of a delay. Listen to the people who know how the machine works.
Stay skeptical, check your seals,
and watch the temperature out